Hello students, good evening. This is Sekhar from Msigma Gokulam. Welcome to today's Crux class of fluid mechanics. I already said yesterday the main objective of these Crux classes, Crux synopsis classes, the main objective of Crux synopsis classes is to make you understand the most fundamental concepts in a very crisp manner, in a quick manner, so that too in a structured sequential manner, so that by utilizing these concepts you are learning in the Crux classes, you would be able to attempt the gate questions at the fastest manner. I already said the prerequisite for this Crux classes is I requested you to look into my FM video classes which were uploaded in the Msigma Gokulam app. Already I had given around 60 hours of class of fluid mechanics which is uploaded in the Msigma Gokulam app. Please go through those FM classes before attending these Crux classes, because the main objective, the main idea of conducting these Crux classes is to put the concepts in a more structured and sequential manner, so that you would be at the quickest manner you would be able to answer the gate questions. Yesterday I had explained about the fluid properties, like most important properties: viscosity, dynamic viscosity, kinematic viscosity, etc., and vapor pressure, mass density, specific weight, and all the surface tension, capillarity, everything I had explained, even the bulk modulus, compressibility. So having understood the properties, then I have introduced the fluid pressure concept, how to measure the fluid pressure. The fluid pressure is the normal force exerted by the fluid on any solid boundary. The normal force exerted by the fluid on any solid boundary per unit area is called as a fluid pressure. How to measure that pressure also I had explained you by writing the most fundamental equation called manometry equation. Okay. While writing the manometry equation, I had given the suggestions also how to write the manometric equation. We have to wisely take the datum line. Along the datum line, we have to equate the pressure heads, preferably mentioned in matrix of water. So the prerequisite for choosing the datum line is, the condition for choosing the datum line is, one side of the datum line you must have the continuous mass of the same liquid. Okay. So how to write the manometry equation also I had explained, and then I had given the Pascal's law and hydrostatic law of pressure variation, etc. And then I had given the buoyancy and flotation. And for a completely submerged body like a submarine or the balloon, I had given the conditions for of equilibrium. Okay, there are three kinds of equilibriums you see in completely submerged body. Okay, one is called stable equilibrium, other is called unstable equilibrium, third thing is called neutral equilibrium. For a completely submerged body like submarine or a balloon floating in the air, a balloon floating in the air is a submerged body. A submarine traveling under the sea water is a submerged body. For a completely submerged body, what is the condition, how to fix the condition, whether your body is in stable equilibrium or unstable equilibrium or a neutral equilibrium, what is the required conditions also I had given. What is the meaning of stable equilibrium? If your submerged body, if a completely submerged body like a balloon, if it is given a slight angular displacement, if the body, if there is a restoring couple developed, which will try to get the body back to its original position, it is called as a stable equilibrium. On the other hand, if you give a slight angular displacement to that body, if there is an unbalancing couple or overturning couple develops, which will further increase the angular displacement of the body, it is called unstable equilibrium. On the other hand, if the body, if it is given a slight angular displacement, the body assumes the new position, it won't come back nor overturn, that is called as the neutral equilibrium. What is the required condition for these three distinct equilibrium situations? Here G must be below B. B is the center of buoyancy, G is the center of gravity. Always the location of the G, what is that G called? Center of gravity, must be located below the center of buoyancy B. Then it will be the stable equilibrium. It is a stable equilibrium. This is unstable equilibrium, where in the unstable equilibrium B lies below G, and here B and G coincide. Because there is no couple developed at all. I already said B is the center of buoyancy. How do you go locate the center of buoyancy? Center of buoyancy is the location where the force of buoyancy acts. Center of buoyancy is the point where the force of buoyancy acts. What is the meaning of force of buoyancy? The upthrust. The upthrust exerted by the fluid which is displaced by the body, that is called as the force of buoyancy. According to the Archimedes principle, the force of buoyancy must be equal to the weight of the fluid displaced by the body, and the location where the force of buoyancy acts is called as the center of buoyancy. Force of buoyancy always acts in the upward direction. Where do the center of buoyancy lie? Center of buoyancy lies at the centroid of the volume of the liquid displaced by the body. Okay. So, if B and G coincide, there is no couple developed at all. Simply the body assumes the new position. It is called as a neutral equilibrium. Okay, the three conditions of equilibrium for a submerged body I explained. What is the meaning of submerged body? The total body is completely immersed, totally surrounded by a fluid. It is like example is submarine or a balloon floating in the air. Now I will give the conditions of equilibrium for a floating body. Floating body means ship or balloon or boat. Conditions of equilibrium for a floating body like ship or boat. Supposing this is a symmetrically shaped body floating inside the water. Okay, this is a floating body. Now, if this is the center of buoyancy where the force of buoyancy acts, and this is the somewhere here the center of gravity, which is called where the weight of the body acts. The principle of flotation states that the weight of the body and the force of buoyancy must be equal in magnitude and opposite in direction, and the line of action also must be the same. Then only that floating body will be in a static equilibrium. There are two forces acting. The body is in static equilibrium, which means that both the forces, that is the weight of the body and the force of buoyancy, which are opposite to each other, they must be collinear, equal in magnitude and opposite in direction. Then only body will be in the static equilibrium. Suppose that if the body is given a slight angular displacement like this, if the body is given a slight angular displacement, the location of the G will not change. The location of the G will not change, but the location of the center of buoyancy within the body will change. Why? Why it changes? Because the body is displacing more liquid on its right hand side as compared to the left hand side. Therefore, the new center of buoyancy will be slightly shifted to the rightwards. You are given a slight angular displacement for the floating body. Then this is the force of buoyancy acting through the B1. What is that B1? B1 is the new center of buoyancy. Why it is shifted to rightwards? Because the body is displacing more amount of the liquid on its right hand side, as in the this is a symmetric axis of the body, right? Okay, and this is the center of gravity where the weight of the body acts. And because the body is displacing more liquid on its right hand side as compared to the left hand side, the center of buoyancy location will be shifted to rightwards. Whereas in the submerged body, which I had explained yesterday, the center of buoyancy do not gets displaced with respect to the body. In the completely submerged body like a submarine or balloon, even if the body is given a slightly angular displacement, the location of the center of buoyancy with respect to the body will not change. It stays there only. But in case of a floating body like a ship or a boat, the center of buoyancy position will be shifted like this. And if you extend that new line of action of the force of buoyancy, it will intersect the central line axis of the body at a point called metacenter. Metacenter is the location or the point of intersection of the new force of buoyancy acting through the new center of buoyancy. When it is extended, it will be intersecting the central line axis of the floating body at a point called metacenter. Okay. Okay. So the location of the M, with respect to the location of the G will decide whether a floating body is in stable equilibrium or unstable equilibrium or a neutral equilibrium. I repeat once again. Whether M lies above G or whether M lies below G, that will decide the condition of equilibrium for a floating body. For this situation, if you just look at this carefully, there are two equal and opposite forces acting at a distance. Therefore, there will be a restoring couple developed. Which is try to get back the floating body to its original position. Therefore, it is called as a stable equilibrium. That means that there is a restoring couple developed. The body would like to get back to its original position after giving the slight angular displacement. This is a angle of heel. Theta is called as a angle of heel. Theta must be tending to 0. Very small angle of heel. You can think of that. So the required condition is, what is the required condition? G must lie below M. What is that M called? Metacenter. What is the meaning of metacenter? The new force of buoyancy acting through the new center of buoyancy will be intersecting the central line axis of the body after the body is given a slight angular displacement. So this is called as a stable equilibrium. If M lies below center of gravity G, implies the floating body is in unstable equilibrium. That means overturning coupled will be developed. That means the body will, the angular displacement further will increase, and there is a possibility, there is a danger of overturning. So that will happen if the M lies below G. If M and G coincide, the body assumes new position because there is no couple developed. It is called as a neutral equilibrium. For a floating body to be neutral equilibrium, the location of M and location of G must coincide. For a small angle of heel, the distance between G and M, GM is called metacentric, as theta tends to 0. For small angle of heel, GM is called metacentric height. Okay. If G coincides with M, then there will not be any couple developed. The floating body will assume the new position. Therefore, the condition of equilibrium for a floating body is decided based upon the relative locations of the center of gravity G and the metacenter M. Okay. The distance between G and M is called as the metacentric height. For a submerged body, the relative locations of B and G will decide. For the floating body, the relative locations of G and M is the metacenter, will decide whether a floating body is in stable or unstable or a neutral equilibrium. What do you mean by unstable equilibrium? There will be a overturning couple will be developed. Whereas here, see, this is a restoring couple for which M lies above the G. Okay, now the situation must be very clear, right? That is the reason why in the boats and ships, to keep the G at the lowest location for all conditions of running of the boat, because when a boat is moving inside a sea or a ship, there is a lot of wind forces will be acting on that. Boat will be moving, tilting like this in so many directions. So keeping the safety of the boat in mind, they would like to maintain the G location at the bottommost position, for which they keep some artificial masses at the base of the ship, which are called as the ballast. The ballasts are the artificial masses kept at the base of the ship so that the location of the center of gravity is always maintained below the metacenter, so that the stability of the body can be maintained for the floating body, etc. Those artificial masses are called as the ballasts. Right. Now, this is the conditions of equilibrium for a floating body. Now, let me do some kind of a problems here which are left yesterday, which some more problems I am going to do. To measure the pressure head of the fluid, this is a problem on the manometry. See, this is a problem on the manometry. Specific gravity, yes. This is the liquid of a specific gravity, yes, flowing through a pipeline. This is a pipeline, a simple micromanometer containing a fluid of specific gravity S1. This is the specific gravity S1. Is connected to it. The readings are as indicated in the diagram. The pressure head in the pipeline here. Okay. The pressure head, this is S1 is the specific gravity. The pressure head in the pipeline will be, and whether the pressure head in the pipeline, in what kind of the fluid is mentioned, but I will take in terms of the the flowing liquid. Yes, that pressure head of liquid flowing in pipe will be. Now I will take the gauge pressure head here in terms of liquid of specific gravity. Yes. Now I would like to write in terms of this liquid. Okay. Now it is 0 gauge. We are going down. That is by what distance we are going down? H1 plus delta H. H1 plus delta H. That is the H1 plus delta H, that is in terms of this liquid, into S1 by S. Okay. This gives the liquid here up to here at this, because they are at the same location. Now we have done up to here. Now we are going up. Minus. We are going up, right? Minus. How much distance is that? Delta H plus H. Minus delta H plus H into, we don't have to convert because we want to write in terms of that S only. Okay, this is answer. Okay. This is in terms of the liquid of specific gravity, yes. The pressure gauges G1 and G2 installed is the previous gate question. Installed show the pressures of PG1 here 5 bar and G2 as 1 bar. Okay. The value of the unknown pressure P, atmospheric pressure, has been given here. Here the atmospheric pressure will be is equal to 1.01 bar, right? With reference to this G2 is recording, how much G2 is recording? 1 bar. This is recording 1 bar. That means if the atmospheric pressure is 1.01 bar and this pressure is 1 bar, then what is the absolute pressure here corresponding to this absolute pressure? 1.01 plus 1. That is because any gauge pressure with reference to the surrounding atmospheric pressure. Surrounding atmospheric pressure is 1.01, whereas here the pressure is 1 bar. Then what is absolute pressure here? It is 2.01 bar. But this G1 is recording how much? 5 bar. This is recording 5 bar. So that is with reference to this 2.01 bar. Therefore here the absolute pressure will be with reference to this one, because for this particular chamber this is a local atmosphere. What is the local atmosphere here? 2.01, but it is recording 5 plus 2.01, that will be 7.01 bar. So answer is D. See, any gauge, if it is measuring certain gauge pressure, is with reference to the surrounding atmosphere. For the gauge reading G1, what is the surrounding atmosphere? 2.01 bar. Whereas for the for this gauge G2, what is the surrounding atmosphere? 1.01 bar. It is 1.01, it is showing 1 bar. Therefore, absolute pressure in this chamber, it is 1.01 plus 1, that is 2.01 bar. So for this gauge G1, this will become the local atmospheric pressure because it is connected into that. Therefore, the pressure, absolute pressure in this left hand side chamber will be, it is showing 5 bar with reference to the 2.01. Therefore, 2.01 plus 5, that is 7.01 bar. Okay. So whenever a gauge is recording certain value, it is with reference to the local surrounding atmosphere. For the G1, the local surrounding atmosphere will be 2.01 bar. It's showing 5 plus 2.01, 7.01 bar. Oil in a hydraulic cylinder is compressed from an initial volume. Oil is any oil is a liquid which is an incompressible fluid. For an incompressible fluid, what is how did I mention? The bulk modulus of elasticity will be very, very, very high because the molecules are closely spaced. Any liquid by default can be considered as an incompressible fluid for which your density is practically a constant because its bulk modulus of elasticity value is very, very, very high. Compressibility is low. Okay, here, what is the bulk modulus of elasticity formula? Change in pressure divided by change in volume divided by original volume. It is compressed from initial volume to final volume of the changes from 40 to 80. That is P2 minus P1 by V1 minus V2 divided by V1. This is the answer. So if you substitute, this is P2. P2 is 80. P1 is 40. Initial volume V1 is 2. V2 is 1.96. Substitute all the values. You will get the answer of the bulk modulus of elasticity. Simple question. In the space above the mercury column in a barometer tube. What is first of all a barometer? Barometer is a device which measures the local atmospheric pressure. Barometer is a device which is meant for measuring the atmospheric pressure. Simply it contains a glass tube open at one end, closed at the other end. It is put in usually it is put in a mercury. Mostly mercury is the barometric fluid. So the height of the mercury rising with reference to this free surface will indicate the value of the atmospheric pressure head. This is the atmospheric pressure head in terms of the mercury column. Okay. Usually if this experiment is conducted at the mean sea level, if this experiment is conducted, it will be recording 76 centimeters of Hg at MSL. MSL means mean sea level. But because as we go to higher and higher altitudes, this pressure will be decreasing. In an isothermal atmosphere, the pressure decreases exponentially. In an isothermal, assuming that the temperature of the atmosphere is same, as we go from the ground to the higher locations, the local atmospheric pressure keeps decreasing exponentially. Remember that. In an isothermal atmosphere. Then what your question is, in the space above the mercury column, what is present here? That means it is a perfect vacuum. Why the mercury is selected as a barometric liquid means because mercury has very low vapor pressure. Mercury has very, very low vapor pressure. It has got very high density. Specific gravity of the mercury is 13.6. Okay, high density and very low vapor pressure, which makes it a suitable barometric liquid. Here what is present? It is a perfect vacuum. Because the mercury has very low vapor pressure, there may be one few molecules of mercury may be there, little, because mercury has a high cohesive forces. Mercury vapor pressure is very, very low. That is why it is used in the thermometers also, because of that reason. The mercury is also a thermometric fluid, not only a barometric fluid. Here it is the gauge pressure of the vapor is 0. Look at that. The gauge pressure of the vapor is perfect vacuum. It is a perfect vacuum. Nothing is there. Nothing is there, you can say. Perfect vacuum, nothing, perfect vacuum. That is also called Torricelli's vacuum. This is also famously known as Torricelli's vacuum, because this experiment is also known as the Torricelli's equipment, Torricelli's apparatus. So this is the problem on the hydrostatic forces on the plane surfaces. The barrier, there is one barrier here between two water tanks. This is one water tank, this is another water tank of unit width 1 meter into the plane. This width will be 1 meter into the plane of the paper, is modeled as a cantilever. This barrier, you take it as a cantilever. It can be thought of as a cantilever. You know the cantilever means fixed at one end and free at the other end. You know the cantilever in the Santa materials. Cantilever is a beam which is fixed at one end and the free at the other end, like this. This is fixed, you can think as this is fixed and free there. But both sides of the barrier are subjected to the water, but one side, which is 4 meter, and other side is 1 meter. Taking the density of the water as 1000 and acceleration due to gravity as 10, the maximum absolute bending moment developed in the calculator in this cantilever. What is the maximum bending moment? So he has combined the problems of strength of materials and with the fluid mechanics. First, let us calculate what are the hydrostatic forces acting on this side of the barrier because of this water. How much is there and where is it acting? I want to know how much hydrostatic force, number one, and where that hydrostatic thrust is acting, at what height it is acting from this fixed end. This is we can think it as similarly, at what location? This is the hydrostatic force, right? So first let me calculate what is F1. I can call this as F2. F1 will be to calculate hydrostatic thrust on the left hand side on LHS because of the water. What is the formula? Hydrostatic thrust for this is a vertical plane, WA x bar. WA x bar. W is a specific weight, A is the area of the plate, and x bar is the depth of the center of gravity below the free surface. This is a free surface, right? So F1 will be W. I can take it as the 9.81, but he has given the that is 10 kilonewton per meter cube. Because he has given kilonewtons, here actually specific weight of water is 9.81 precisely, but he has given that taken as the 10 there. So 10 kilonewton per meter cube is the specific weight. What is the formula for the hydrostatic thrust? Yesterday I had given WA x bar. W is the specific weight of the liquid, A is the area of the plate, and x bar is the depth of the center of gravity below the free surface. So this is W. What is the area? Area will be 4 meters and this depth will be 1. 4 into 1 area of the plate, because up to here only you have to take, water is there. This is 4, this is 1, this dimension, because he has given unit width into the plane of the figure. That means this dimension is 1, WA into x bar. That is x bar will be 4 by 2. This is so many kilonewtons, right? Now where does it act? Question is, where does it act? That means for a vertical plate, supposing first I will give this, for a vertical plate, I want to calculate, supposing if this is immersed like this, it is a free surface, and if this is the height h, and this is a base B, rectangular plate, if you see that, this will be the h by 2. The location of the center of pressure here, center of pressure, this will be the h bar. What is that h bar? Depth of the center of pressure below the free surface. First I am deriving the formula. I am just deriving the formula for a rectangular vertical plane. Where do the center of pressure lie? From the free surface. These. So this is x bar, we can say. This is x bar, that is h by 2. H is the height of the plate, rectangular plate, B is the width. So what is the formula? H bar is equal to x bar plus Ig by Ax bar. What is the x bar? X bar will be h by 2. Ig is the area moment of inertia about the center of gravity. This is the center of gravity, right? This is the center of gravity. The depth of the center of gravity will be h by 2. That is called x bar. What is that x bar? That's the depth of the center of gravity below the free surface. That is h by 2. Cp is the center of pressure where the total pressure is acting, like this. Total pressure, how much it is acting, we have calculated. But where it is acting, that is acting at the center of pressure, right? So I am calculating the location of the center of pressure below the free surface. That is this h bar I am calculating. H by 2 plus Ig. Ig will be the BdQ by 12. That is the formula for the moment of inertia. Ig is the moment of inertia about the centroidal axis, right? That is B h cube by 12. Area will be B into h into x bar will be h by 2. So it becomes this h cube and this gets cancelled, B will get cancelled, and this h square will becomes cancelled, that is it will become h. So h by 2 plus h by 6. If you take the LCM 6, 3h plus h, that is 4h by 6, that is 2 by 3 h. 2 by 3 h from the this is we got it as the 2 by 3 h from the top. So therefore from this below, from the below, what is this distance? When this is 2 by 3 h, it will be 1 by 3 h from the base, because I want to calculate the bending moment based on this one, okay, from the below. So this height will be, how much will be the 1 by 3 h. That means this distance will be 1 by 3 into height will be here how much? 4 by 3 meters, right? Now fine. Then what is F2? I calculate F2, hydrostatic force on the right hand side. Hydrostatic force, this is one of the gate question, previous gate question. This is hydrostatic thrust on RHS. What is the formula? WAX bar. What is the WAX bar? W is 10. Area will be right side. It will be 1 into 1. Area of the plate will be 1 into 1. At what distance center of gravity that? At what distance of half of the 1 meter? That is 1 by 2. So many kilonewtons, right? So that is on the F2 right hand side. If so, where it is, what will be this depth? Again same formula, 1/3 of the higher, 2/3 from the top. Based on that, it is 2/3 from the top. This is the formula I have derived. So what is this distance? 1/3 from the height, 1/3 into 1. Now I can calculate very easily the bending moment. So if you just take the cantilever like this, right hand, this will be 1 by 3 total height, 1 by 3 from the here. This is F1, this will be the F2, F1 will be acting at what distance from this? This is the fixed point, right? This is the location here. F1 is acting, that is 4 by 3 meters. This will be acting at 1 by 3 meters. So, one is clockwise and another is anti-clockwise. We can calculate net bending moment. Net bending moment is equal to F1 into 4 by 3 minus, this is one is clockwise, another is anti-clockwise, minus F2 into 1 by 3. So many kilonewton meter. You can easily get the answer. Okay, first we have to calculate F1 and F2, that is the hydrostatic force acting on the left hand side and the right hand side. And where is it acting? They are acting at a distance of 4 by 3 meter from the cantilever fixed end and 1 by 3 meter from the cantilever fixed end from the right side here. This distance will be 1 by 3, this distance will be 4 by 3. So, this formula I have derived if a rectangular plate is immersed in a liquid, so that the free surface is exactly matching with the top of the rectangular surface. At what distance, at what location that center of pressure will be there? It will be located at a distance of 2 by 3 h from the top or 1 by 3 h from the bottom. So, that is what I have taken. 1 by 3 into height, 4 meters from the bottom, 1 by 3 into 1 meter. This is 1 meter given there. So, I have calculated the location of the center of pressure and how much is the total pressure, based on which I have calculated the net bending moment. So, this fixed end is same as this. This is the end here. F1 acts here and F2 acts here. One is clockwise and the other is anti-clockwise bending moment. Okay. So, very good question given in the gate. Yeah, this is also a previous gate question. Previous gate question. This is a pressure measurement device fitted on the surface of a submarine. Submarine moves beneath the sea water, right? Located at a depth h meters below the surface of an ocean. This is the ocean. There is a submarine. Okay, h meters below the ocean, submarine is traveling. This is a free surface. This is all the ocean. Reads an absolute pressure of 4.2 megapascal. Here, one pressure measuring device, it is reading an absolute pressure of 4.2 megapascal. It is reading. The density of the sea water is slightly more than the pure water. Pure water is 1000, but sea water contains salts, slightly more denser, that is 1050 kg per meter cube. Atmospheric pressure is 101 kilopascal. Here the atmospheric pressure is 101 kilopascal and the acceleration due to gravity is given 9.81. The depth h will be. Very simple question. If this is atmospheric pressure, I already said absolute pressure is defined as gauge pressure plus atmospheric pressure. Atmospheric pressure is given, absolute pressure is given. If you can get the gauge pressure, how to calculate the gauge pressure here? W of the seawater multiplied by the depth. Because I already said yesterday, if you want to know the any liquid is there, if you want to know the gauge pressure inside that liquid whose depth is known, just multiply the specific weight of that liquid with the depth of the point. You will get the gauge pressure at that location. Gauge pressure means what? The pressure in excess of the local atmospheric pressure. We know that this is atmospheric pressure. In excess of that, how much will be the gauge pressure is given by W into H. There is some liquid is there. Inside the liquid at one point we have selected. We know the depth of that point. If you want to calculate the gauge pressure at that point, just multiply the specific weight of the liquid with the depth of the point. That will give the gauge pressure. Okay. What is the absolute pressure? Atmospheric pressure plus this gauge pressure. Okay. Now, P absolute pressure, how much is given? 4.2 megapascal. Means 4.2 into 10 cube kilopascal is equal to gauge pressure is how much? W of the seawater into depth plus 101 kilopascal. What is the W there? W is equal to rho g. We know that W is equal to rho g. Okay. Rho is 1050 into G is 9.8, but that will be in Newton per meter cube. So I just divide with 1000 so that you will get in kilonewton per WH should be in kilopascal, right? W into H should be in kilopascal. But whereas 1050 into 9.81 it will give the pascal. So I want the answer in kilopascal. That is why it, because this is also kilopascal, from which no, this is a W into H. This is W into H plus 101. We can easily calculate. This will be 4.2 into 10 cube, from which we can calculate the H. Only you have to be extra careful with the units, because W value is W is equal to rho g. As long as the rho is kg per meter cube and g in meters per second square, acceleration due to gravity, this will be in Newton per meter cube. But I want to convert into the kilonewton per meter cube. That is why I have divided it. W units will be Newton per meter cube. But I want to keep it in kilonewton per meter cube, so that the answer, this answer I have to get it in kilopascal. This answer I have to keep it in kilopascal, because this is in kilopascal, this is in kilopascal, this also should be kept in kilopascal. That is why the W value I have to get it in kilonewton per meter cube. That is why I have divided with 1000. Okay, take care of that, and you will get the answer of the H in meters there. You should be very careful about the units while doing the problems of FM, fluid mechanics. Okay. The difference in pressure across an air bubble of diameter 0.001 meters immersed in water. This is a water. There is an air bubble. This is an air bubble. Sigma is a surface tension. Okay, given that, what is the difference in pressure? Okay, this is air bubble. It's all water, right? It's all water. So P gauge, already yesterday discussed 2 sigma by R. It is just similar to the water droplet kept in air. Water droplet. Now this air bubble kept in water, both mean the same. That is 2 into sigma value is 0.072 divided by 0.001 divided by 2. So many pascal. This is the answer. Newton per meter square. This situation and this situation is same. This is a water droplet. Now it's all surrounded by air. Here air bubble surrounded by water. Both mean the same, similar situation. Gauge pressure. What is the meaning of gauge pressure? How much is the pressure here is more than the outside pressure. That is called as the gauge pressure. How much the pressure inside this air bubble is more than the outside pressure, it is called as the gauge pressure, right? Now the dimensional formula for the surface tension, sigma is in Newton per meter, that is ml T power minus 2 divided by length. So it will be m into T power minus 2. This is the answer. If P is the gauge pressure within a spherical droplet, the gauge pressure within a bubble of the same fluid and of the same size will be P. One is for droplet, it is 2 sigma by R. Another thing will be, this is for the droplet, this is for the bubble. Bubble will be, what is the formula? 4 sigma by R. That will become 2p. Answer is D. He is asking within a bubble of the same fluid and of the same size. Then kinematic viscosity is given at 20 degrees Celsius. Its kinematic viscosity at 70. So as with for gases, remember for gases, as temperature increases, kinematic viscosity also will increase. Only probable answer is D. It will increase. Okay. Assuming constant temperature condition and air is an ideal gas. Ideal gas means P by rho is RT. Okay. And the variation of atmospheric pressure with height. We know that dP by dz is equal to minus rho g. If you substitute that one there, keeping that T as a constant, and if you integrate, you will get the answer as exponential. P varies exponentially with respect to the height. P decreases exponentially with respect to height in an isothermal atmosphere. T is constant. You can treat this as constant. Okay. Instead of rho, we can substitute that P by RT and separate the limits, separate the variables P and Z and integrate. You will see that the pressure decreases exponentially with height in a constant temperature. Isothermal means what? What do you mean by isothermal? Isothermal means constant temperature. Okay. This is an ideal gas equation. Air is an ideal gas. An incompressible fluid, kinematic viscosity is given 7.4 into 10 power minus 7 meter square per second. The kinematic viscosity. Specific gravity is also given 0.88 held between two parallel plates. Held between two parallel plates and bottom plate is stationary. Okay. While the bottom one is held stationary and the top plate is moved with a constant velocity of 0.5 meters per second. Okay. The fluid attains a linear velocity profile. The gap is given here. The gap is given as 0.5 mm. There is a linear velocity profile obtained for the fluid. The bottommost layer has got a zero velocity. The topmost layer will have the same velocity as that of the plate, that is 0.5 meters per second. Okay, the shear stress in Pascal on the top surface of on the top of the plate. What is the shear stress here? Now I will bring in the Newton's law of viscosity. Tau is equal to mu into dou u by dou y. The shear stress is directly proportional to the velocity gradient. If u is the velocity, because the gap is very small, you can write this as mu into v by y. Because he has already clearly given a linear velocity profile. Because it is a linear velocity profile, dou u by dou y, this is a y direction, can be written as v by y. Because velocity is changing linearly from the 0 to the 0.5 meters per second. Therefore, dou u by dou y can be written as v by y. V by this gap, this v divided by y. Because since it changes linearly. But what is mu? Nu into density into v by y. That is the shear stress. But do you know the density? Density is not directly given, but he has given the specific gravity. Specific gravity means what? What is specific gravity? Density of the fluid divided by density of the water. Density of the water I know, that is 1000 kg per meter cube. Therefore, shear stress is equal to kinematic viscosity is 7.4 into 10 power minus 7. Take care of the units there. 10 power minus 7 meters per second, and rho will be 0.88 into 1000. That is the density of water, because this is 0.88. Yes, sir. And rho is equal to 0.88 into density of water. Now we have written what is the velocity there. Velocity is 0.5 and the gap is 0.5 mm, but we should consider it in meters only. 0.5 divided by 1000. So this is the answer given in Pascal. You will get the answer. This is the shear stress. And is the shear stress, he has asked the shear stress on the top plate. Now I will extend on the surface of the top plate. But is the same shear stress is acting on the bottom plate also? This is the shear stress we have calculated. Viscous stress, tangential stress, all mean the same. Shear stress or the viscous stress or the tangential stress all mean the same. This is the shear stress we have calculated on the top of the plate. Okay, shear stress, that means shear force per unit area. Is the same shear stress acting on the bottom plate also? Yes, because see in this formula, all the parameters are same. No, nu, rho, v, y. So the shear stress is between any two fluid layers. Shear stress between any two fluid layers, it is same. It is same shear stress here, and the bottom plate also. That point also. Supposing instead of the top plate, if he has given the bottom plate, answer will be the same again. The shear stress between any two fluid layers which are moving one above the other, it is same throughout the gap. That point you can notice. It is also the previous gate question. A solid block of 2 kg mass slides steadily at a velocity of v. It is sliding down with a velocity v along a vertical wall as shown in the figure below. This is a figure. This is a vertical wall. A thin oil film of thickness 0.15. This is 0.15. This is all oil film. This is oil. This is all oil film. Thin oil film provides a lubrication between the block and the wall. As the block is sliding downwards, the gap between the wall and the block, it is filled with the oil. All this is oil. The surface area of the face of the block in contact with the oil film is 0.04 meters square. This area of the block in contact with the oil has been given. Surface area of the block in contact with the oil, this area was given as 0.04 meters square. The velocity distribution within the oil film gap is linear. See that velocity is, here the velocity is 0. Here the velocity of the oil layer, it is same as the velocity of the block. It is linear, very clearly given. It is linear, mentioned that. See that velocity distribution. Dynamic viscosity of the oil is given. Acceleration due to gravity is given. Neglect the weight of the oil. The terminal velocity of the block is. With what velocity? The terminal velocity means with what velocity the block will be sliding downwards. So on the block, if you just look at the block, on the block what are the forces that are acting? One is weight of the block, which is nothing but the mg, mass into acceleration due to gravity. There is one more force here, upward force, that is the shear force or the viscous force. Shear or the, because shear stresses or viscous stresses are shear in nature. Okay, upward. So both the forces must be cancelling out each other. Therefore, the net force acting on the block is 0. Acceleration is 0. Therefore, it is sliding downwards with a constant velocity v. How much is that constant velocity? he has given. Oh, you have to calculate that. You have to, terminal velocity is how much? Because acceleration is 0. Why acceleration is 0? Because the weight of the block is exactly balanced by the upward tangential force, viscous force. Since, I am writing here, since block slides down with constant velocity, V, net force on block is 0 because its acceleration is 0, because it is sliding down with constant velocity. Rate of change of velocity is acceleration. Velocity is constant, therefore acceleration is 0. When acceleration is 0, according to the Newton's second law of motion, F is equal to ma, net force must be 0. That is, what are the two forces? mg should be equal to the viscous force acting upwards. What is viscous force? Stress into area. What is the viscous stress according to the Newton's law of viscosity? Mu into dou u by dou y into area. Because the velocity is changing linearly, I can write dou u by dou y as mu into v by y. Instead of y, I am writing h here. Actually, this is a h or y. This dimension, you can take it as the y direction. So v by dou u by dou y, you can write it as v by h. Because velocity is changing linearly here. You can clearly give it in the figure. He has mentioned here also. V by h into area. So you can easily get the answer. M is how much? Mass is 2. G is 9.81. Dynamic viscosity has been given there. Viscosity of the oil. You see that? 7 into 10 power minus 3. Terminal velocity, we don't know. H has been given as 0.15, but that should be converted into the meters. All dimensions we have to keep it in meters. Into area. What is the area in contact? 0.04. So you will get the answer. Velocity in meters per second. As long as you correctly substitute the units of each physical quantity, the final answer also will be correctly equal to. See that? Velocity in meters per second. This is a block on which two forces are acting. One is weight, another is shear force. That is why it is sliding down with a constant velocity. You will get the answer there. mg is in newtons. Therefore, dynamic viscosity also I should substitute in Pascal second. Pascal second means, what is the meaning of Pascal second? Newton second per meter square. Okay. It is also previous gate question. A cubical block of side L and mass M. This is a cubical block of side L. Is dragged over an oil film across the table by a string which connects to the hanging block. A cubical block, this is an oil. Gap between this table and the block is filled with oil whose dynamic viscosity is mu, and the block is sliding over the oil. The other one string is connected to the block, and the other side of the string is carrying a mass M. The Newtonian oil. What do you mean by Newtonian oil? The fluid which obeys the Newton's law of viscosity, for which mu is constant. A Newtonian fluid like water, air will have a constant dynamic viscosity mu. A Newtonian fluid is that fluid for which the dynamic viscosity remains constant. Right? Newtonian film of thickness h has a dynamic viscosity and the flow condition is laminar. Acceleration due to gravity given, the steady state velocity v of the block is. Now if we just look at this block, it is moving with a constant velocity. That means acceleration is 0 because it's moving with a constant velocity for the block. When acceleration is 0, how many forces are acting on that? How many forces are acting? One is tension in the string, pulling it rightwards, and other thing is the viscous force here. Viscous force in the opposite direction and tension is. So, for the block, there are two forces are acting, tension in the string and opposing force will be viscous force, and this is the M. Okay. And because it is a string, this tension should be same as this one, right? Because it is moving with a constant velocity, this also should move with a constant velocity because it is a connected body. String means a connected body, right? So, on this, this M is going downwards. So, for this M, how many forces are there? One is mg, upward is tension T, but it is moving with a constant velocity. So, okay, it is moving with a, that means implies T is equal to mg. This tension is mg because acceleration is 0. For this small m also acceleration is 0 because whatever the acceleration of this, same is the acceleration. It is moving with a constant velocity means it is also moving with constant velocity. Acceleration is 0 means only two forces. One is mg, upward force is tension. So, T should be equal to the mg. This is mg, small mg. Okay. Now, this T must be equal to the viscous force here. What is the viscous force? T should be equal to the mg, should be equal to the viscous force, that is stress into area. Stress will be how much? Mu into, according to the Newton's law of viscosity, it is dou u by dou y, mu into dou u by dou y into area. But because gap is very small, Newtonian fluid, gap being very small, you can think it as a linear velocity variation. Therefore, I can take that as the V by H, that is tension T is equal to mu into V by H. I could write area will be L square. See that this is a L, this is L. This is the area of contact will be the L into L square. Okay. Now the tension will be how much here? Tension will be already mg this is. So from which what is the velocity we may get the answer? Velocity V will be mgh by mu into L square. C is the answer. Answer is C. So I have written the equation of motion for this mass first. Because it is moving with a constant velocity v, the tension must be equal to the mg. The same tension I have put up here, that is mg acting rightwards, and whereas the opposing force will be the viscous force. Viscous force will be stress into area. What is the area of contact? L into L. Because the bottom face of the cube will be L into L square. So that is the area of contact between the block and the oil. Area of contact between the block and the oil is L square. Now I got the velocity of the sliding of the block. Very good question. This is given in the previous gate. Look at this. In a simple concentric shaft bearing arrangement, it is also previous gate question. Concentric shaft it's something like a journal bearing. This is a shaft is rotating inside a bearing. This is the axis of the shaft. The lubricant flows in the 2 mm gap between the shaft and the bearing. This is a bearing. This gap will be the 2 mm where you have the lubricant oil. Oil is there in this 2 mm gap. The flow may be assumed a simple lubricant flows here. The flow may be assumed to be a plain coative flow with zero pressure gradient. Plain coative flow. One coative flow means one is stationary, one plate is stationary and other plate is moving. That is called as the cohesive flow. Diameter of the shaft is 100 mm and its tangential speed is 10 meters per second. Diameter of this span. And the dynamic viscosity of the lubricant is given frictional resisting per 100 meter length. This is the 100 mm length of the shaft. Tangential speed is 10 meters per second. Okay. The gap being very small, we may assume that the velocity variation is linear. We can think of that. Okay. The frictional resisting force. Radius of the shaft is 50 mm. This is 50 mm. Okay. Stress is equal to mu into dou u by dou y. That is a Newton's law of viscosity. Mu into tangential velocity divided by gap. This is the gap. This is the gap, right? That stress will be mu into V by Y, and stress will be force by area. Mu into V by Y. Area will be force divided by area will be pi d into height, length. This is 100 mm length is how much? 100 mm. Pi d into length into mu into V by Y. V is given, Y is also given. V is 10 meters per second, Y is 2 by 1000 meters to mm, that is, and diameter of the shaft is 100 mm, length of the shaft is 100 mm. Everything you have to keep it in meters there. Substitute everything there, you will get the force. Force in newtons. Okay, area of contact is pi d into length. That is the area of contact between the bearing and the oil. Okay, but keep everything in meters. That is, d will be 0.1 meter, length will be 0.1 meter, everything meters there. Velocity should be 10 meters per second. Mu is 0.1. Mu will be 0.1 kg per meter second or 0.1 Pascal second. Pascal second is same as the kg per meter second. Every dynamic viscosity value we have to substitute only in Pascal second or kg per meter second. Okay, you may substitute this mu value here. Velocity is given, y is given, y is this gap. This is the gap is y, which is given as the 2 mm and I have converted into the meters there, 2 by 1000. See, lubricant flows in the 2 mm gap here. It is also the previous gate question given. So, I have solved the most of the problems given in the previous gate pertaining to the fluid statics, manometry, hydrostatic forces, viscosity problems, bulk modulus, everything. All the first fluid statics problems, everything I have done, including manometry. Okay. Now, I will start the fluid kinematics, very, very important chapter. The most important chapter in the fluid mechanics It will be the fluid kinematics. Most important. Among all the chapters, is the highest weightage I give. First of all, in the fluid kinematics, we do not deal with the force. We don't talk about the forces acting on the fluid element, but fluid is in motion. We will be describing the motion, we will be analyzing the motion without bothering about the forces that cause the fluid motion. If you bring the forces into a picture, that will become the fluid dynamics. Now I am doing the fluid kinematics. But in the fluid kinematics, there are two kinds of analysis. But what is the fluid kinematics? Analysis of the fluid motion in terms of the displacement, time, velocity, acceleration, a stream function, velocity, potential, describing the flow, okay, and what are the various types of acceleration, convective acceleration, local acceleration, normal acceleration, tangential acceleration, all these things describing the motion in terms of displacement, time, velocity, acceleration, without bothering about the forces that cause the motion. I don't bother about the force. But if I bother about the force, if I try to account for the forces acting on the motion and then connect the motion with the forces, that becomes a problem of fluid dynamics or the Euler's equation of motion, Bernoulli's equation, all that will come. Before that, this is the kinematics. In the kinematics, there are two kinds of the analysis of the motion. One is called as the Lagrangian analysis. The second thing is called as the Eulerian analysis. In the Lagrangian analysis, an individual fluid particle will be selected and we will be following that fluid particle in due course of time during the motion. And what are the changes in velocity, displacement, acceleration, etc. occurring for that point. Like that we do for many fluid particles. Okay, we will be selecting a fluid particle. We will be following that particle and what are the changes that occur in velocity, displacement or acceleration for that fluid particle in due course of time as it flows, we will be analyzing. Like that you do it for the many particles. So that is called as the Lagrangian analysis, but we don't bother. We do not do that Lagrangian analysis in our entire fluid mechanics. Rather, we will do the second analysis called as a Eulerian analysis. Leonhard Euler is the very founding fathers of the FM, okay, who is a contemporary student of Bernoulli, Leonhard Euler. That Eulerian analysis says that we don't follow the fluid particles. Rather, we will be fixing a particular space coordinate in the fluid flow regime. We are considering one point, one location with a known space coordinates x, y and z space coordinates. We will be selecting a particular location in the fluid flow regime and what are the changes that would occur in the velocity, displacement and acceleration at that particular location which is selected in the fluid flow regime, we will be analyzing. It is called as the Eulerian analysis. Okay. I repeat once again, in the Eulerian analysis, we will be selecting a particular location in the fluid flow regime with a known space coordinates, x, y, z in the fluid flow regime. This is x coordinate and y coordinate. And this is a z coordinate maybe. And what are the changes that would occur in the velocity, displacement, acceleration at that point we will be analyzing. That is, this kind of analysis is called as Eulerian analysis. Okay. Like that we will be doing at many locations in the fluid flow control volume or fluid flow regime. Okay. So for that we should first define what is the velocity of fluid particle. If we just select one particular location P with known coordinates x, y, z, if a fluid particle at that location is undergoing a displacement delta s in a time interval of delta t seconds tangential to the streamline. I will define what is the streamline later. If a fluid particle at location P with a known space coordinates x, y, z is undergoing a displacement delta s tangential to the streamline in a time interval of delta t seconds, then the velocity of the fluid particle is defined as differential calculus based on the delta s by delta t as delta t tends to 0, which can also be called as a ds by dt. This is the definition of the velocity of the fluid particle. A fluid particle at location P is undergoing a displacement delta s tangential to the streamline in a time interval of delta t seconds. Then this is the definition of the velocity. You know, velocity is a vector quantity which has got both magnitude and direction, and that direction of the velocity will be the tangential to the streamline. That is same as the direction of the displacement vector. Okay. This velocity v must be definite. Being a vector, it should be having the three components. Based on your vector mechanics, where u, v, w are the three mutually perpendicular components of the velocity vector. I bar, j bar, k bar are the unit vectors along x, y and z directions. Okay, u, v and w are three mutually perpendicular components of velocity vector along x, y and z directions. What are that u, v, w? They are the three mutually perpendicular components of velocity vector along x, y and z directions. Obviously, that magnitude of the velocity vector will be square root of u square plus v square plus w square. Okay. Now I defined the velocity. Now having defined the velocity and having defined the velocity, now how do you get that UVW? I would like to define that UVW also. Based on the vector mechanics, if this delta s has got a component delta x and delta y parallel to the x and y directions, what is that delta s? Delta s is the displacement. Delta x and delta y and delta z being the components of the displacement vector delta s parallel to x, y and z direction component will be delta z. Then u will be velocity component, u will be limit delta x by delta t as delta t tends to 0, which can be written as dx by dt. Dx by dt is the velocity component of the fluid along x direction. That means the rate of change of the rate u is what is basically u? U is the velocity component of the fluid along the x direction, parallel to the x direction. It can be defined as the time rate of change of x direction component of the displacement with respect to the time. The time rate of change of the derivative of the x direction component of the displacement, with respect to the time is the x direction velocity. So you should be understanding as the time rate of change of x direction component of the displacement, that is delta x, it is called as the velocity component along x. Similarly, v will be limit delta y by delta t as delta t tends to 0, that becomes dy by dt. That is the time rate of change of y direction displacement component, of the displacement vector with respect to the time. The time rate of change of y direction component of the displacement vector is called as the y direction component of the velocity. Same way w will be there in the similar lines. the z direction component of the velocity will be the dz by dt. What is the dz? The time rate of change of z direction component of the displacement. This displacement vector has three components, one along the x, one along the y, and other along the z. So we have but now we have understood what is the meaning of the velocity and its components u, v, and w. Okay, we know that. We know very well defined the components of the velocity vector. Okay, now having understood the velocity and also its components, we know how to define the components of the velocity vector along x, y, and z now. Now I will define what are the various types of the fluid flow. First of all, in kinematics, we should understand various types of the fluid flow. I mean steady and unsteady flow, uniform and non-uniform flow, laminar and turbulent flow, rotational and irrotational flow, compressible and incompressible flow, one-dimensional, two-dimensional, three-dimensional flow. So in this classification of the fluid flows, one must have a very strong idea. Then only you will be able to understand the entire FM. Now I will describe all these fluid flows. Classification of fluid flows. First and foremost important, it will be steady and unsteady flows. Steady, what you should understand, what is the meaning of steady flow and unsteady flow. See, in the fluid flow regime, the fluid is flowing maybe inside a pipe. If at any particular point, if you select in the fluid flow regime, if various fluid flow characteristics like pressure, density, velocity, etc. Generally, what are the fluid flow characteristics? These are the parameters which will be used to describe the fluid flow. What are the most of them will be velocity, pressure, density, etc. Right? These are the various fluid flow characteristics. If those characteristics at a particular location in the fluid flow regime do not change with respect to the time, it is called as a steady flows. Steady flow means things will not change with respect to time. This word steady, we will see it in thermodynamics, we will see it in heat transfer, we will see it in FM, we will see it in turbomachinery, thermal turbomachineries. But at so many contexts, we talk about this steady flow. Steady means things will not change with respect to the time, no time dependency. So, for example, fan is flowing through the air is flowing through the fan. Air is flowing through a ceiling fan. It is running with under the same regulator 3. Things are normal. Nothing is changing. I can say air is flowing under steady state conditions through that ceiling fan which is rotating with a constant velocity in the 3 regulator mode. I can say that flow of the air through that ceiling fan, I can treat it as the steady. Steady means at a particular location, fluid flow parameters, fluid flow characteristics must not change with respect to time. Like it may be velocity, it may be pressure, it may be density, whatever the fluid flow parameters. So that is called as a steady flow. That means velocity at a particular location in the fluid flow regime is not a function of time. Supposing if you see some velocity here, the fluid particle moving in that location, moving in that direction with 10 meters per second. So neither its magnitude of that velocity nor the direction of the velocity is not changing with respect to time at that particular location. I am not saying that the velocity here and here it is same. I am not saying. The velocity here and the velocity here may be different. But at a particular spot, at a particular location, the various fluid flow parameters must not change with respect to time. Now, if you see 10 meters per second, say for example, after 5 minutes or after 20 minutes also, the velocity must be the same as 10. That is called as a steady flow. On the other hand, if velocity becomes a function of time, transient it is called. That means now at this moment 10 meters per second, after a few seconds, after 1 minute, the velocity may be different, something else, it is called as an unsteady flow. Then it is called unsteady flows. Unsteady flows are very uncommon. We don't see generally most of the problems in fluid mechanics and also fluid flows in thermodynamics also. We treat them fluid flows as steady. Most majority of it. I don't say that unsteady flows will not be there. There will be unsteady flows also, we'll be analyzing, but the cases are less as in the examination also. Okay, this I think I hope you understood the meaning of steady and unsteady flows. In steady flow, the mass flow rate m dot is the mass flow rate, mass flow rate of fluid is constant. Second thing will be, second classification I am giving, uniform and non-uniform flows. Uniform and non-uniform flows. In uniform flow, uniform means at every location, at every spot, at every location, we must see the same velocity value. Same velocity at every point to point. Uniform means what? Same value of the velocity for every fluid particle at every location. The velocity of the fluid is not a function of space or location. At every location, we must see the same velocity. Now, for example, if you see the 10 meters per second here also 10 meters per second, here also 10 meters, everywhere. At every location you must see the same velocity at any given instant of time. At any given instant of time, if various fluid flow characteristics fluid flow characteristics do not change from location to location, do not change from location to location, such flow is uniform. But look at this, velocity is not a function of space or the location. That means if you see one velocity here, different velocity here, different velocity here, it is called as a non-uniform flows. If velocity becomes a function of space or location, it is a non-uniform flow. I would like to tell you one important thing, that here a flow can be steady, but at the same time it can be non-uniform. A flow can be uniform, but at the same time it can be unsteady. Any probability is there. A flow can be steady, but at the same time it can be non-uniform. A flow could be uniform, but at the same time it can be unsteady. I will give the 4 examples here. For example, a flow of a fluid in a converging passage with a constant flow rate. It is the example for the steady flow but non-uniform. Steady flow but non-uniform flow. Why? Why it is a non-uniform flow? The velocity here V1 and the velocity here V2, V1 is not equal to V2. Definitely I can say that V1 is not equal to V2, but whatever the velocity you see here, after 5 minutes also you will see the same velocity at that location. It is a non-uniform, but the flow is steady. Now I will give another example. A long constant diameter pipe with a constant mass flow rate. A long duct, flow through long duct at constant mass flow rate. It is an example for steady uniform flow. Mass flow rate remaining constant. That means whatever the velocity you see here, same velocity you see here. Not only that, whatever the velocity you are recording here, 10 meters per second, say for example, after 10 minutes also, after 20 minutes also, you will see the same velocity here. Flow is steady and as well as uniform. Uniform means you will see the same velocities, same pressures at every spot in the fluid flow regime. And if the things at a particular location do not change with respect to time, that is a steady. Now, I will give another example. Supposing here the mass flow rate is not constant. It is a unsteady, non-uniform flow. At a particular location, velocity is changing from time to time. And also, at any given instant of time, the velocity here and the velocity here are different. The velocity is changing with space, and also velocity is also at a particular location, velocity may be changing with time. It is an unsteady and a non-uniform. Okay. Now, it is a steady uniform constant mass flow rate. Now, it is a long duct, but mass flow rate is not constant. It is a unsteady flow. M dot is a symbol for the mass flow rate. Unsteady flow, but uniform flow. Unsteady flow, but uniform. A long duct, a constant area duct, mass flow rate is not constant. That means, if you see the velocity here, 10 meters per second, now at this moment, here also at the same instant of time, it is 10 meters per second. After 15 minutes, if the velocity here is 20 meters per second, here also it will be 20 meters per second. Velocity is same at every location, but at a particular point, the velocity is changing with time. It is unsteady, but uniform. Okay. So, all the possibilities are there. Now, having understood the two types, now the third important thing is rotational and irrotational flows. This is a very important classification. If the fluid particles, while traveling in the fluid flow regime, do not rotate about a fluid particle while translating in the fluid flow regime, if it does not rotate about its mass center, it simply translates. The fluid particles are simply translating from one location to the another location. the fluid particles are not rotating about their mass centers. Such flows are called as the irrotational flows. This is a very important classification in FM. On the other hand, if various fluid particles rotate, if the various fluid particles rotate about its mass centers while translating in the fluid flow regime, it is called as the fluid particles, it is translating, but at the same time it is rotating. And why that rotation happens? Why do this rotation of the fluid mass will happen about its mass center? It is just because of the viscous nature of the fluid. The prime and the main reason behind the rotation of the fluid mass about its mass center while translating in the fluid flow regime. Translating means what? Going from one location to the another location. The fluid particles, while translating from one location to the another location, at the same time they keep rotating about its mass center. Such flows are called as the rotational flows, the main reason being the viscous nature of the fluid. So the real fluid flows, the viscous fluid flows, real fluid means a fluid having viscosity. Only an ideal fluid will have zero viscosity. Every fluid, real fluid will have more or lesser viscosity. So by default, all the real fluid flows are rotational flows. Irrotationality is something like an ideality, imaginary, because for the flow to be irrotational, we have to neglect the viscous forces. But how come that would be possible? Because every fluid will have some more or lesser viscosity. So irrotational flows are can be thought of as some idealized flows or inviscid flows, where the viscosity of the fluid is neglected. Okay, this is a very important classification. Then how do you say a given fluid flow is rotational or irrotational? Means there are certain conditions are there. Say for example, velocity potential function must satisfy the Laplace equation, or the stream function must satisfy the Laplace equation given in size. So there are certain mathematical conditions required to call a particular fluid flow as irrotational. Say for example, certain rotation components are there, omega x, omega y, omega z. When all the three rotation components about the x, y and z axis become zero, such fluid flows can be thought of as irrotational flows. But irrotational flows are ideal fluid flows, potential flows. We can all different names. Irrotational flows are idealized flows or the potential flows. They also be called as the potential flows, because velocity potential function exists only for these irrotational flows. So I will define what is the velocity potential. So this is one other classification. Next classification will be very important classification, that is laminar and turbulent flows. Please note that I had given the detailed videos which are available in the Msigma Gokulam app. I had given about 60 hours of fluid mechanics class, which is uploaded in the Msigma Gokulam app. You may go through that app and see my fluid mechanics videos, because I suggest all the students to please go through those videos before coming to these Crux synopsis classes. Okay, Crux conclusion synopsis classes these are. So the main idea of covering taking these Crux classes will be to give a very quick review, putting the subject in a very structured and very cohesive and rational manner. I would like to put the subject so that for a quick revision, for a quick understanding of the subject, to quickly attempt the questions in the gate, these Crux classes are very much useful. Okay, but we condition that, subject to the condition that before attending these Crux classes, I request all the students to please go through those the video which are given uploaded in the Msigma Gokulam app by me. For the full coverage of the detailed coverage of the fluid mechanics videos are available there. First go through them, and then if you come to the Crux classes, it will be quite useful, because you will be able to recollect and wisely connect those concepts which I had given explained in detail in those fluid mechanics videos. Okay, just take a small break for 5 minutes. 55, huh? Hello students, welcome back to this Crux class. Now I had given the classifications of irrotation and rotation. Now I am going to give the classification regarding the laminar and turbulent flows. It's a very important classification in fluid mechanics. If various fluid particles travel in laminae, as the flow is happening, if the fluid particles travel in laminae with one layer of the fluid smoothly sliding over its adjacent layer without any intermingling. If one layer of the fluid is smoothly sliding over its adjacent layer without any intermingling or intermixing of fluid particles among the fluid layers, such flows are called laminar flows. The other name of the laminar flow is viscous flows. The other name of the laminar flow is viscous flows, because what makes the fluid particles travel in streamlines, travel in straight lines, what will control the disturbances means the viscous nature of the fluid. What makes the fluid particles to travel in laminae? Lamina means a layer. What makes the fluid particles to travel one behind the other in lines, actually, like this, means the main reason is viscous nature of the fluid. Viscosity controls the disturbances in the fluid flow or fluid motion of the fluid flow particles and make the fluid particles to travel in laminae. That is why laminar flows are also known as the viscous flows. On the other hand, in the turbulent flows, there is continuous intermixing, continuous intermingling, continuous mix-up, continuous turbulent means continuous intermixing or intermingling of fluid particles among the fluid layers. As the fluid is undergoing motion, there is a continuous turbulence will be there. There will be a continuous mass transfer, momentum transfer or energy transfer happening among the fluid layers, because fluid masses keep jumping from one layer to the another layer. It is called as a turbulent. Then when do you say a given fluid flow is laminar or turbulent? How do you identify? Means there is one of the most important dimensionless number which we speak about in the fluid mechanics called as the Reynolds number. This number is there in not only in fluid mechanics but also in the heat transfer. Reynolds number, RE, defined as the ratio between inertia forces and the viscous forces. Reynolds number is a dimensionless number defined as the ratio between inertia forces and viscous forces. This number is the criteria to tell whether a given fluid flow is laminar or turbulent. If you calculate Reynolds number, it has a formula VD rho by mu, or inertia force by viscous force, and based on by looking at the value of the Reynolds number, I will tell you later. By looking at the value of the Reynolds number, you will be able to make out, you will be able to judge whether the flow is laminar or turbulent. Okay, defined as the inertia force by viscous force. This is the definition of the Reynolds number. A criteria to tell a laminar or turbulent. Okay, and I hope you understood that. In the laminar flow, fluid particles travel in laminae, whereas in turbulent flow, a continuous intermixing, zigzagness, intermingling among the fluid layers. As the fluid particles travel, they keep jumping from one layer to the another layer, carrying more mass, momentum and energy with them as such. So that is one of the important classification. Then comes the compressible and incompressible flows. Incompressible and compressible flows. If the density of the fluid is not a function of pressure, or if density of the fluid remains constant, such flows are called as incompressible flows. All liquid flows, example, or by default, all liquid flows are incompressible. All water, any liquid flows. If the density of the fluid becomes a function of pressure, that is, density is not constant, if the density of the fluid is changing from location to location during the flow, if the density of the fluid changes, it becomes a function of the pressure. It is called as the such flows are called compressible fluid flows. Example, all gas flows at very high velocities. I cannot say any gas flow is a compressible. Supposing the flow of air through a ceiling fan, I will treat it as the incompressible. I don't treat it as the compressible because the density changes of the air as it flows through the ceiling fan, it will not be even 1%. So 1% change or 2% change in the density of the flowing fluid can be neglected, and density can be treated as a constant, and the flow can be branded as incompressible. So I mean to say here is, even the many gas flows, if they are running at low velocities like a flow of the air through a ceiling fan, can be treated as incompressible because very little changes of density can be neglected, and the density can be treated as practically a constant. Therefore, I mean to say that a compressible fluid flow domain requires a gas flow particularly running at very high velocities. I told you also earlier, last class also, Mach number. As long as the Mach number of the fluid flow is greater than or equal to the 0.3, the compressibility effects of the fluid flow comes into picture, and that flows can be treated as compressible. Okay. Example, all gas flows, all gas flows with Mach number greater than 0.3, greater than or equal to 0.3, or if density changes are more than 5%. As long as the density changes of the fluid during the flow is greater than, more than 5% or equal to 5%, yes, we can treat it as the compressible fluid flow. Otherwise, even the gas flow is also can be treated as incompressible. That is, density is practically a constant in the incompressible flows. So these are the main things. And another thing is one-dimensional, two-dimensional and three-dimensional flows. If velocity is a function of only x direction, okay, like this. If the velocity changes only in the x direction, in the other two directions, if it is remaining constant, that is called as the one-dimensional flow. If velocity becomes a function of both x comma y, like this. If the velocity changes both in the x and y directions, it is called as the two-dimensional flows. Okay. On the other hand, if the velocity becomes a function of all the three coordinates, x, y, z coordinates, such flows are called as three-dimensional flows. And mostly in the exams, in the fluid mechanics exam, mostly you will give the two-dimensional flows. Mostly 90% cases in the gate examination, you will give the two-dimensional flows, not the three-dimensional, not the one-dimensional. In the three-dimensional flows, that means the velocity keeps changing in all the three directions along x, y and z directions. That is a three-dimensional, this is one-dimensional, this is two-dimensional. Okay. So I have classified the fluid flows, and now I will define the very important definition called as a streamline. What is a streamline? Streamline is most of the questions in the gate, they ask about the streamline. Streamline equation. Streamline is an imaginary curve drawn in the fluid flow regime in such a way that the tangent drawn to the streamline at any particular location will give the direction of the velocity vector at that particular point. Streamline is an imaginary curve drawn in the fluid flow regime. Fluid flow regime means the location, the area where the fluid flow is happening. Streamline is an imaginary curve drawn in the fluid flow regime in such a way that the tangent drawn to it at any particular point will give the direction of the velocity vector at that point. Supposing if you just draw the tangent here to the streamline, that gives the direction of the velocity vector for the fluid particle at that location. If you just draw the tangent here to the streamline, that would give the direction of the velocity vector of the fluid particle at that particular location. Now, if you just take the component for the velocity vector along the x and y directions, this will become u. This is v. Okay. Now, if this is the tan theta, the slope of the streamline is equal to dy by dx is equal to v by u, or dx by u is dy by v, or v dx minus u dy is equal to 0. This is the equation of streamline. Questions on streamline are very common in the GATE examination. U and V are the components of the velocity vector along x and y directions. So, by integrating this equation, we may get the equation of the streamline. Okay. In steady flow, I already mentioned, in steady flow, the things will not change with respect to time. In steady flow, various parameters remains fixed constant with respect to time. That means, if you draw a streamline in the steady flow, they are fixed in space. Now, you have drawn a streamline now. After 10 minutes, you have came and seen. The streamlines are there only. It won't change, it won't shift their position. But in unsteady flow, the streamlines are instantaneous in nature at that particular location only. Streamlines are instantaneous in nature because they keep changing from time to time in unsteady flows. Whereas in a steady flow, they are just fixed in space. Path line. Before that, I'll define the stream tube. Stream tube is an imaginary tube which is totally, completely bound by the streamline. These are all the streamlines. So this is another streamline, right? So stream tube is completely bound by the streamlines. So because there cannot be any component, if you see, there cannot be any component, no component here in this direction, right? Velocity is directed along the tangential. Therefore, in the normal direction, there is no component for the velocity vector. Therefore, no flow across stream tube. No flow in this direction. Whatever the flow happens, only along through the stream tube. No flow across the stream tube, because no flow in this direction. Because all the flow must happen through the stream tube. Path line. Path line is, it is the line traced out. Path line is the line traced out by a single fluid particle at successive instants of time during the course of the flow. Streamline is supposing at t is equal to 0 seconds, particle is here. At t is equal to 1 second, particle is here. At t is equal to 2 second, so it is the line traced out by a single fluid particle during successive instants of time during the course of its travel, during the course of time. If the streamline is indicating, repeat, if the streamline is indicating the velocities of various fluid particles, if the streamline is indicating the velocities of various fluid particles at different locations at a given instant of time, if the streamline is indicating the velocities of various fluid particles at different locations at a given instant of time, it is indicating the velocity. See that streamline is indicating the velocities of various fluid particles located at different positions but at a given instant of time. But path line is indicating the velocities of a single fluid particle at successive instants of time. Now, after 1 second, after 2 seconds, after 3 seconds, like that. Okay. Whereas streamline is indicating velocities of various fluid particles located at different locations but at a given instant of time. For steady flows, streamlines and path lines are identical. Whereas for unsteady flow, streamlines are different, path lines are different. Similarly, there is one more line called here streak line. Generally, in the fluid mechanics, it is a common practice to add a dye. I will add one dye here. One color, one dye I will add at this location, and the fluid particles passing through that point, okay, at t is equal to 0 seconds, particle is here. At t is equal to 1 second, this particle has moved here. But at t is equal to 1 second, another particle has entered here. At t is equal to 2 seconds, this particle has moved this way. At t is equal to 2 seconds, this particle would have come here. Like that. That means the path traced out, the line traced out by a fluid particle passing through a fixed point, that is called as a streak line. Streak line is a line traced out by various fluid particles passing through a fixed point in the flow regime where the dye may be added. Try to understand that. At t is equal to 0 second, one particle has been added here. At t is equal to 1 second, that particle has come here. At t is equal to 2 seconds, that particle has travelled to this location. But at t is equal to 0 second here, 1 second here, after 1 second. But at t is equal to 1 second, there is another particle is here, right? At t is equal to 2 seconds, this particle has moved only this point, right? This is 2 seconds. So that means we have to join at the end of the 2 seconds, if we join these two, that is the streak line. At t is equal to 2 seconds, at t is equal to 3 seconds, say, where is the various particles passed through a fixed point? If you join all of them, you will get the streak line. For in steady flow, streamlines, path lines and streak lines all are identical. Whereas in unsteady flow, they are different. In unsteady flow, streamlines are different, path lines are different, streak lines are different. In steady flow, all are same. In unsteady flow, streamlines, path lines and streak lines are different. I hope you understood the streak line there. You will be adding a color. So at t is equal to 1 second, where is the particle you will be identifying. At t is equal to 3 seconds, where are the various particles at different passing through this fixed point. We will have to identify all those particles at t is equal to 3 seconds and we join all of them. That will be a streak line at the end of the 3rd second, like that. So at t is equal to 4 seconds, what are the locations of various fluid particles passing through this fixed point? We have to identify various particles. Where are they? and join all of them at the end of the 4 seconds. That is a streak line after 4 seconds, like that. But all the particles will be passing through this point where the dye or the color may be added. Okay, now having defined the streamlines, streak lines, path lines and equation of the streamline, now I will define an acceleration of fluid particle. Acceleration is rate of change of velocity with respect to time. That is limit delta V by delta T as delta T tends to 0. The rate of change of velocity with respect to time is called acceleration. Acceleration is a vector. Just like velocity, acceleration is also a vector. Therefore, this acceleration of the fluid may have 3 components: ax I bar, ay j bar plus az k bar. What are I bar, j bar, k bar? They are the unit vectors along x, y and z directions. Where are the ax, ay and az are the 3 mutually perpendicular components of the acceleration along x, y and z directions. Ax, ay, az are the 3 mutually perpendicular components of the acceleration along x, y and z directions. 3 mutually perpendicular directions. Now, if you want to define acceleration component along the x direction, that is nothing but, according to the differential calculus, the rate of change of x direction component of the velocity with respect to time, that is du by dt. The time rate of change of x direction component of velocity. The time rate of change of x direction component of velocity, that is u, is the acceleration component along the x direction. But in general, we know that u is a function of x, y, z, t. V is a function of x, y, z, t. In general, w is a function of x, y, z, t. Why? Since the velocity itself is a function of, velocity may be different at different locations. At a given instant of time, velocity may be different at different locations, and also the velocity at a particular location may change with the time. So earlier we have defined the velocity, which is a vector quantity. So that velocity at any given instant of time, the velocities may be different at different locations. Here the velocity may be different, here the velocity may be different, here it may be different. So velocity at a given instant of time, velocity may be a function of space, and also at a given instant, at a given location, the velocity may change with time. Understand? If at a given instant of time, different locations in the different flow regime may have a different velocities, and also the velocity at a particular location may change with respect to the time, like in case of steady flow. Like in case of unsteady flow. In unsteady flow, what will happen? At the velocity at a particular location may change with respect to the time. So because the velocity is a function of 3 space coordinate and 1 time coordinate, these 3 are the components of the velocities. Therefore, they also become a function of 3 space coordinates and time coordinate. Now if you just look at this ax, I could write it as, because u is a function of x, y, z, t, I could write that dou u by dou x into dx by dt plus dou u by dou y into dy by dt, dou u by dou z into dz by dt is a function of functional rule, dou u by dou t into dt by dt. Okay, mathematically we could write like that. But what is the dx by dt? What is the dx by dt? U into dou u by dou x. What is dy by dt? V, right? V into dou u by dou y. This is w. W into dou u by dou z plus dt by dt is 1. Dou u by dou t. So this is the acceleration of the fluid along the x direction, which comprises, this is the acceleration of the fluid along the x direction, which comprises two different components. One is called as this part is called as the convective acceleration of fluid along x. This is called as the convective acceleration. What is the meaning of convective acceleration? Convecting means one location to the another location, change in position, that is called as a convective. If the velocity component of the fluid along x direction, that is u, it is changing from one location to the another location at a given instant of time, that is accounted by this convective acceleration of the fluid. Whereas this particular part is called as the local acceleration. Local acceleration of fluid along x. You have to thoroughly understand these definitions. This is the local acceleration, this is the convective acceleration. In uniform flow, I already mentioned, in uniform flow, at every location, at every spot, the velocities are same. That means in uniform flow, the convective acceleration along any direction must become 0. This must be 0 in uniform flow, because in uniform flow what means what? At every spot you must see the same velocities, right? So in uniform flow convective acceleration is 0, but in steady flow local acceleration is 0, because at a steady flow means what? The parameters must not change with respect to time at a given location. In steady flow this will become 0. In uniform flow this convective acceleration along any direction becomes 0. Now in the similar manner I could write ay. What is that ay? The acceleration component along the y direction, that is u into dou v by dou x, v into dou v by dou y, plus w into dou v by dou z plus dou v by dou t. This is here, this sum is called as the convective acceleration. This particular thing is called as the convective acceleration along y. Whereas this last one, this is called as the local acceleration of the fluid along y. Please note that this dou v by dou t is the local acceleration of the fluid along y direction, which will become 0 if the flow is steady. In any steady flow, the local acceleration along any direction becomes 0. Whereas this is called as the convective acceleration along the y direction, which will become 0 if the flow is uniform. Please note that. I am writing here. In uniform flow, the convective acceleration of fluid, the convective acceleration of fluid along any direction becomes 0. Whereas in uniform flow, whereas in steady flow, the local acceleration of fluid along any direction becomes 0. I have given the x and y, I have write the az also, acceleration of the fluid along the u into dou w by dou x plus v into dou w by dou y. W is the z direction component of the velocity vector plus dou w by dou t. This is the acceleration of the fluid along the z direction. Earlier thing was the acceleration of the fluid along the y direction. This is the acceleration of the fluid along the x direction. If the streamlines, see, the velocity of a fluid particle is always tangential to the streamline, but the acceleration, which is also a vector quantity, may not be along the tangential to the streamline. Velocity of the fluid particle will always be tangential to the streamline. That is how we define the streamline, right? But the acceleration of the fluid need not be along the streamline. Okay, so that is why it may have the one tangential component of the acceleration may have the two components. One is the tangential component of the acceleration, and other thing is the normal component of the acceleration. These tangential components, this accounts for change in magnitude of the velocity vector. Change in magnitude of velocity vector with respect to time. See, velocity is a vector quantity. It has both magnitude and direction. If the magnitude of the velocity changes, I say that there is acceleration. If the direction of the velocity changes, again I say that there is an acceleration. So, the velocity of the fluid has two different modules. One is direction and other thing is the magnitude, because velocity being a vector. If the magnitude of the velocity vector changes, I say that there is acceleration. That acceleration which is arising out of the change in magnitude is called as the tangential acceleration. Whereas this accounts for change in direction of velocity vector with respect to time. If the direction remains constant, if the magnitude changes, then I say that yes, there is tangential acceleration is there. If the magnitude remains same, but the direction magnitude remains same, but the direction changes, yes, still I say that there is an acceleration will be there. Okay. A converging streamlines like this, no? A converging streamlines will have convective tangential acceleration. Supposing if the streamlines are like this, no convective normal acceleration, and no convective tangential acceleration, no acceleration at all. If the streamlines are converging like this, there will be a normal acceleration will be there. There will be a convective acceleration will be there. If the streamlines are symmetric like this, there will be a normal acceleration will be there. If the streamlines or curvature, both it will be convective acceleration will be there, normal acceleration will be there. Convective, there will be a convective tangential acceleration and convective normal acceleration. Here there will be a convective, normal acceleration, convective normal acceleration, there will be a convective tangential acceleration here. Here in this case there is no acceleration at all, no acceleration at all. So the streamlines straight but converging, yes, there will be acceleration. Streamlines are concentric but having a different radius, yes, there will be again acceleration. Streamlines are curvilinear and converging, yes, there is again a acceleration. If the streamlines are straight, there is no acceleration at all. So any possibility is there. A converging curvilinear straight streamlines, a converging straight line streamlines, yes, there is acceleration here. A concentric circular streamlines, yes, there is an acceleration here. Just 1 second. So, okay, coming back to the class. Now, if the streamlines are converging straight like this, it is a convective tangential acceleration. Convective means At different locations, different velocities. Convective means from spot to spot, if you go, you have a difference in velocities, that is called as a convective. This is a convective normal acceleration. Here, both convective tangential and normal acceleration. Here no acceleration at all because is a straight line streamlines. So we have got different situations. This is a convective normal acceleration, convective tangential acceleration. Here both convective, tangential and acceleration because it is a curvilinear converging streamlines. It is a curvilinear symmetry, concentric streamlines. Concentric, this is a convective normal acceleration. It is a straight streamlines but converging. They are a convective tangential acceleration. Convective means, see, when you talk about the acceleration, I am using the word convective and local. Convective means at a given instant of time, if the velocity is changing from spot to spot or direction is changing from location to location, it is called as a convective. Okay. So the velocity has a two modules, magnitude and direction. If the magnitude changes, we say that there is acceleration. That acceleration that arises because of the change in magnitude is called as a tangential acceleration. Similarly, the velocity has got different module called direction. So magnitude remaining same, but the direction is changing. That means that particular change in direction of the velocity is accounted by normal acceleration. So one is tangential acceleration, another is normal acceleration. So this is a convective tangential acceleration, this is a convective normal acceleration. Here both convective, tangential and normal accelerations, here no acceleration at all. So this is how various ways of indicating the streamlines. Now I will define the most important equation in fluid mechanics called continuity equation or conservation of mass. Because on this there are so many questions will come in the gate. Conservation of mass, law of conservation of mass. Mass can neither be created nor destroyed. When a fluid flow is happening in any pipe, if this is the area A1, section 1 this is section 2, this is area A2, velocity V2, here the velocity V1, the flow is happening like this. According to this continuity equation, the rate of mass entering the control volume must be equal to the rate of mass leaving the control volume. The rate of mass in steady flow, the rate of mass entering control volume should be equal to the rate of mass leaving control volume during steady state operation, during steady flow. That is, m dot remains constant. M dot is the mass flow rate. That is rho 1 A1 V1 is equal to rho 2 A2 V2. But if fluid is incompressible, what do you mean by incompressible? That is rho is equal to constant. When rho is equal to constant, I could cancel these two, implies A1 V1 is equal to A2 V2, or AV, that is called as the Q, which is known as the discharge or volume flow rate. Discharge or volume flow rate of fluid must remain constant in meter cube per second. What is that AV product called? Area into velocity. A is the area of flow, V is the velocity. That area of flow must be perpendicular to the direction of flow. Remember that area of flow and the direction of the velocity must be perpendicular. This equation is called as a continuity equation or conservation of mass. Rho AV is constant or AV is constant, both mean the same. Rho AV is constant. If because flow is incompressible means Rho is constant. When rho is constant, the product of AV will be the constant. But this is in the finite form. But in differential form, for three-dimensional steady or unsteady, compressible or incompressible, compressible or incompressible fluid flow. But in in a differential form, for three-dimensional steady or unsteady, compressible or incompressible fluid flow, continuity equation is given by, it is a generalized format. This is the steady or unsteady, compressible or incompressible. If the flow is steady, this is a generalized format of the continuity equation. Rho is the density of the fluid, U, V and W are the velocity components, U, V and W are the velocity components of the fluid along X, Y and Z directions. Rho is the density. If flow is steady, dou rho by dou t becomes 0, no time dependency, because things will remain constant with respect to time. And if flow is incompressible, density is also a constant. Then the rho is constant, means rho can be taken out. That becomes dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is the format of the continuity equation for what kind of flow? For 3D, for three-dimensional steady incompressible fluid flow. This is the format of the continuity equation for three-dimensional steady incompressible. This can also be written mathematically vectorially as divergent V is equal to 0. This is the continuity equation. This is the continuity equation for three-dimensional steady incompressible flow. This is one of the gate question asked lesson. Very important conservation rule, because in any fluid mechanics problem can be solved with the three conservation principles. Any fluid mechanics problem. One is conservation of mass or continuity equation, which I have given here. Second thing is conservation of energy, which is also called as the Bernoulli's theorem or Bernoulli's equation, which I will see later. Number 3 is a conservation of momentum, which is also called as the impulse momentum equation. Any fluid mechanic problem can be solved with these three conservation rules: conservation of mass, conservation of momentum and conservation of energy. Okay, so the conservation of momentum is also can also be called as Newton's second law of motion. Okay, that I will show it later. Now, having seen this, now I will define two important scalar functions known as velocity potential and stream function. Velocity potential, I will define two scalar functions. Phi is a scalar function of space and time. Space and time defined as such, defined as phi is a scalar function of space and time, defined in such a way that whose negative derivative with respect to any direction will give the component of the velocity vector along that direction. Whose negative derivative with respect to any direction will give the component of the velocity vector along that direction. This is the defining expression for phi. Phi is a scalar function of, what is the name of phi? Velocity potential function. It is a scalar function of space and time defined in such a way that whose negative derivative with respect to any direction will give the component of the velocity vector along that direction. What is the component of the velocity vector along x? U. What is the component of the velocity vector along the y? That is v. Similarly, if you take the derivative, partial derivative, mind that it is a partial derivative. Dou phi by dou z is a w, velocity component along the z direction. So, this velocity potential function phi exists only for the irrotational flows. One of the very important question. Velocity phi exists only for the irrotational flows. Okay. That is why irrotational flows are also called as the potential flows. Phi exists only for irrotational flows. Hence, irrotational flows are also known as potential flows. Potential flows, ideal flows, irrotational flows all mean the same. Now, if we just now I deduced a continuity equation. What is that? Three-dimensional continuity equation I have written for steady flow. Dou v by dou y plus dou w by dou z is equal to 0. If we substitute this u, v, w there, that is dou by dou x of minus dou phi by dou x plus dou by dou y of now it becomes dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0. This is called as Laplace equation in phi. This is the Laplace equation in phi. That means any velocity potential function phi, that satisfies the Laplace equation in phi, any velocity potential function phi that satisfies the Laplace equation del square phi is equal to 0 will correspond to some sort of irrotational flow. That is very important point. I would like to say here that, once again I repeat, any velocity potential function phi that satisfies the Laplace equation del square phi is equal to 0 will correspond to some sort of irrotational flow. any velocity potential function phi that satisfies the Laplace equation in phi, that is del square phi is equal to 0, will correspond to some sort of irrotational flow. That means to prove whether a given fluid flow is rotational or irrotational, if you want to prove that a given fluid flow is rotational or irrotational, what we have to do? Check for that fluid flow whether it satisfies the Laplace equation in phi. If it satisfies, yes, we can declare that flow as irrotational. If it does not satisfy that Laplace equation, yes, the flow is rotational. It is as simple as that. For any curve for which if the phi value is constant, that curve is called as the equipotential line. Supposing if I draw a curve in the space coordinate in the xy plane, if the value of the phi is same at every location for that curve, it is called as an equipotential line. So for that I am calculating the slope. Slope of equipotential line on xy plane, that is dy by dx for constant phi, it is equal to minus dou phi by dou x divided by okay. But what is minus dou phi by dou x? That is u. What is dou phi by dou y? This is the slope of equipotential line on xy plane. Okay. Minus dou phi by dou x is u. Dou phi by dou y is minus v. It becomes minus u by v. This is the slope of equipotential line. What do you mean by equipotential line? An imaginary curve for which the value on the xy plane, for which the value of phi is same at every location on that curve. Now I will define another scalar function called as the stream function psi. Two scalar functions are here. One is phi, already defined. Second thing is the psi. Generally, it is defined only for the two-dimensional flows. Psi is a scalar function of, it is generally defined only for the two-dimensional flows. Psi is a scalar function of space and time defined for 2D flows only. Defined for only 2D flows in such a way that like this you have to, if this is x, this is y direction, if you take the derivative with respect to x direction, it will give the component in the counterclockwise direction. Component in the perpendicular direction taken in the counterclockwise. Psi is a scalar function of space and time. Psi is a scalar function of space and time defined in such a way that if you take the partial derivative with respect to x, it will give the component in the perpendicular direction taken in the counterclockwise sense. Similarly, if you take the derivative with respect to y, it will give the component in the negative x direction. What is the component in the negative x direction? Minus u. This is how we define the stream function. both phi and psi both are scalar functions, right? And by looking at this, we may also see that stream function is nothing but a streamline. Stream function is nothing but a curve which is nothing but which is indicating a streamline. Look, you can see that slope of constant stream function line on xy plane. If you just take the slope of constant stream function line, that is dy by dx for constant psi, I could write it as mathematically minus dou psi by dou x divided by dou psi by dou y. Okay. What is minus dou psi by dou x? Minus v. What is dou psi by dou y? Minus u. It becomes v by u. It is nothing but the streamline. It is just nothing but the slope of the streamline which already defined. It is nothing but the slope of streamline. That means I can conclude that, very important conclusion I can give you, that a constant stream function line for which the value of psi is same at every location on that is nothing but a streamline. A constant stream function line is just nothing but a streamline. The other name of streamline is constant stream function line. Look at that. It's we have already given earlier when I defined the streamline 1 hour ago. I have given the slope of the streamline. You could recall. Same is the slope for the constant stream function line. So I can conclude that a constant stream function line for which the value of psi is same at every location is just nothing but a streamline. So if you just and what is the significance of the streamline? Supposing if you just take this, now this is psi 1 is equal to constant, psi 2 is equal to constant. The difference of psi 1 and psi 2 will give the discharge of fluid between these two streamlines is nothing but psi 1 minus psi 2. The difference of these two streamlines values will give the volume flow rate of the fluid passing between those two streamlines. Please remember that. Discharge of a fluid passing between two streamlines is given by the difference of the two streamline values. Okay. Please remember this point also. Earlier, we have seen that the slope of equipotential line minus u by v. Then we have the slope of constant stream function line. Now, if we just take the product of these two slopes, we know the slope of equipotential line, we know the slope of constant stream function line. If we just take the product of these two slopes, we will see what will happen. Dy by dx of constant phi into dy by dx of constant psi. You will get minus u by v into v by u. It becomes minus 1. That means if the product of the two slopes is equal to 1 or minus 1, that those two curves must be orthogonal to each other. Very important point asked in GATE earlier. There are two curves are there. The product of the slopes of those two curves is happening to be 1. That means what do you conclude? Those two curves must be orthogonal or perpendicular to each other. Therefore, I can conclude that Therefore, equipotential lines are orthogonal to constant stream function lines at every location in the fluid flow. At every location in the fluid flow, except at stagnation points. Except at stagnation point. Stagnation means where the velocity becomes zero, except at the stagnation points. Equipotential lines, if you're drawing these are all the equipotential lines or constant stream function lines, you can say. Psi 1 is equal to constant, psi 2 is equal to constant, psi 3 is equal to constant. Now, if you draw the equipotential lines, they will be like this. Phi 1 is equal to constant. This is the meaning of the orthogonal. They cut orthogonally. These are all the equipotential lines. They cut orthogonally. Equipotential lines and constant stream function lines cut orthogonally. Such grid obtained is called as the flow net. Such grid obtained is called as the flow net. That means I want to say that constant stream function lines and constant velocity potential lines or equipotential lines, they cut orthogonally everywhere in the flow field except at the stagnation points. And such a grid obtained is also known as the flow net. So, very important points I have discussed in the kinematics. Questions are very, very common. Most of the questions in FM you expect only in this particular topics called kinematics of the fluid flow. As you see in the previous gate papers also, you will see a very good number of questions on this kinematics of fluid flow. The questions may be asked like this. They may ask you two functions u and v will be given. They will ask you to derive the equation for the streamline, or they will give the two components and ask you to find the third component of velocity provided the flow is existing under steady state conditions, that is continuity equation is satisfied. So, the questions, because it is something connected with the mathematical, this kinematics of fluid flow. Okay. So, the questions on this kinematics are very, very common. I will solve the other questions in the next class. Until then, bye-bye, good night, and please note that before attending these Crux classes, please go through my videos which are already uploaded in the Msigma Gokulam app. This is Sekhar from Msigma Gokulam. Good night.